Today we're talking about sine and cosine as functions, functions with graphs, rather than simply ratios of the sides of a triangle. If you haven't begun memorizing your special angles and radians, this is the time to start. From here on out, we will be using radians predominantly, and converting between degrees and radians takes too long. To start, you should label the unit circle below in radians, and give precise numeric values for sine and cosine at each point. You'll want to write small. See page 286 for a useful table. And what I mean by this is that we're going to label this first angle as 0 and note that its sine and cosine, or cosine and sine rather, are 1 and 0. The next angle we would come to would be pi over 6. It has a cosine value of root 3 over 2, a sine value of 1/2, etc. Continue on. Really, for your own benefit at this point, you should stop the video, go through, complete this entire circle. I have added 4 documents which show the unit circle broken up into families of angles. You may want to take a look at those. They shed some light upon the patterns that are present inside of the unit circle, and it's kind of fun. Right. With your unit circle complete, let's look at graphing the different values for sine that appear around the circle. We'll use angle measure as our independent variable. Now, when we were at angle 0, we had a sine value. We're looking at sine, right? We had a sine value of 0. Let's scroll back up and take a look at that. Yes. So angle 0 had a sine value of 0. So that means, if we're looking at this coordinate plane, that when the angle is 0, my sine value, which we've said is going to be the dependent variable, would also be 0. So we'll have a point right there. Now, by the time we get to pi over 4, we would have been at root 2 over 2. And that is a little harder to graph, so let's keep on going. If we go out to pi over 2 has a sine value of 1. So we'll add a point up there. Let's keep on going out. Pi has a sine value of 0. Similarly, 3 pi over 2 has a sine value not of 1, but of -1. And finally, 2 pi has a sine value the same as 0 of 0. We could also think of travel in the negative angle direction. That is, if we were traveling like so. And that would mean that negative pi over 2, right there, also right here, negative pi over 2 would have had a sine value of -1. Okay, now we said that pi over 4 had a sine value of root 2 over 2. Now the decimal approximation of that is 0.7. So at pi over 4, we should be looking to see a value right about, let's see, 0.6, 0.5, yeah, right about there. Let's clean up a little schmutz. And 3 pi over 4 has the same. When we get down to 5 pi over 4, it becomes negative 0.7. 7 pi over 4, still negative. And negative pi over 4, kicking back over to this area, would have also had a sine value of -0.7. Oops, wrong spot. There we go. And these start to highlight the behavior of our graph. If we connect our points smoothly here, this gives us a good image, and you can expect that the curve would continue, of the sine of x. We've talked enough about period, amplitude, etc., to go ahead and get some information down for this. The period of this function, the distance from peak to peak, right? Now we haven't done a full peak to get to another peak. Our next peak would be over here. But what we can note is that one full cycle happens between those two dashed lines. So that looks like a period of 2 pi. The amplitude of this function, that is the height that it rises above the midline, is 1. And the midline itself is happening at y equals 0. Now, the next thing we need to talk about is a flashback. It's the idea of even and oddness within a function. Remember, a function is even if f of negative x is equal to f of x, and it is odd if f of negative x is equal to the opposite of f of x, so negative f of x. Now, we could consider this function and note that the sine of negative pi over 4 is equal to, well, it's not equal to the sine of pi over 4, so that must mean that it is not even, but the sine of negative pi over 4 is equal to negative onto the sine of pi over 4. So that means that this function is odd. Now, let's do the same thing with the values of cosine from your unit circle. Cosine is different. Let's scroll back up and take a look at that circle. The cosine value happens right here. So the cosine of 0 is 1. So that means if we're letting cosine be our y-axis and the angle measure be our x-axis, cosine of 0 being 1 happens right there. After that, things continue more or less as we might hope. The cosine of pi over 2, the x-coordinate, is actually 0. And the cosine of pi will be negative 1. The cosine of 3 pi over 2, it's again 0. And finally, the cosine of 2 pi is 1. We can look towards the negative values as well, and we would find that the cosine of negative pi over 2 is 0. Now remember, pi over 4 has the property that cosine and sine are in fact equal. So we can plug in that same convenient 0.7 value right there. And similarly at 3 pi over 4, also 5 pi over 4, and at 7 pi over 4. We can go back to negative pi over 4. Now, interesting, negative pi over 4 has a positive cosine value. Remember, negative pi over 4 lives here, which means that its cosine corresponds to a positive x-axis position on the unit circle. So the cosine value for negative pi over 4 is that positive 0.7 again. Okay, now let's connect all of these smoothly. Smoothly enough, anyhow. And again, we should talk about the period, the amplitude, the midline, and even odd behavior. The period is once more 2 pi. This time we get a really nice view from peak to peak. The amplitude is 1. The midline once more happens at y equals 0. And the function is going to be even. Now, why am I able to say that right off the bat? Remember, even or odd, even would mean that f of x was equal to f of negative x. Well, what we just discussed was that the cosine of pi over 4 is equal to the cosine of negative pi over 4. And this function behaves in that way consistently. So we are even. Shiftiness. It's time to move things around. What was the effect of the transformation f of x plus 5 back in the day, back when we were talking about generic functions? What about 5 times f of x? Might be worth looking those up. Pause the video if it's helpful. F of x plus 5 was a vertical shift up 5. We took the whole function, whatever its center was formerly, we bumped it all up 5. And 5 times f of x, this was a vertical stretch. So that leads us to a question of how these transformations would behave with regard to sine or cosinus functions. What is the amplitude of g of x equal to 5 times sine x? Well, if 5 on the outside acts as a vertical stretch, then it should be taking our function, which was happily living at -1 and 1, doing that little number, and it should take the whole thing, take the peaks and pull them down, pull them up. So stretch, stretch to 5. The interesting thing with the cosine is that not only do we get pulled up to 5, we also get pulled down to -5. And the real thing there is that the amplitude is what is impacted by that vertical stretch. So the new amplitude is now 5. Now, next, what are the amplitude and the midline of h of x equals 5 sine of x plus 5? Well, we just said that the 5 on the outside, right here, was a vertical stretch and that it meant that the amplitude became 5. So the amplitude, we already can say, amplitude is 5. But the midline, they're asking about the midline. Well, plus 5 means we have a vertical shift up 5. That means that the center of our original function got shifted up 5. So if we're thinking about the cosine function, or not the cosine, but the sine function rather, the center of that function is its midline. And that means while the original function would have had a midline at 0, the new function now has a midline at 5. So the amplitude of this transformed function would be 5, and the midline would be y equals 5. Last point of discussion. Find a function that describes the height of a point P above the x-axis as a function of the angle theta for a circle of radius 5 and center 0, 5. This all feels very complicated, but it's not. And to clarify that, we should sketch the circle that this is talking about. So it's telling us that our circle is centered at 0, 5. Great. There's and I've got radius 5. Okay, so then that's another point on my circle, and that's a point on my circle, and that's also a point on my circle. Also one up here. So yeah. Okay, we'll call that good enough. Now, the angle theta is the independent variable. The height is the dependent variable. So if that's a start point, then when theta equals 0, our height equals 5. So I'm going to start sketching a graph of this. This will be the height axis. This will be the theta axis. So when theta is 0, we're saying that height is 5. Let's move our way along. So if we move up to an angle of pi over 2, that at this stage, we've got a height now of 10 above the x-axis. So 2, 3, 4, 5. That looks like it's up there. Now, if we move another pi over 2, so this gets us around to pi on rotations. That brings us back to 5. And if I move another pi over 2, oh, that's interesting. That actually brings me down to 0. Huh. So at 3 pi over 2, I'm all the way down to there. And then bringing it on home, when I finally get out to 2 pi, I am back up to 5. So if we were to draw this, try and connect it smoothly, oh, voila. That, my friends, is a sine function. In fact, it's precisely h of x from up above. This is a sine function, so we'll just call it f, that has amplitude of 5. You can see that right there to the midline. We know it's sine because it starts on its midline, as opposed to starting above its midline as cosine does. And its midline has been shifted up 5 units. And there's our equation.